right, so what we want to do today is we want to kind of continue on with what we were looking at on Monday. And so Monday we ended with kind of looking at kind of the beginnings of describing elements and defining isotopes. And I wanted to bring up kind of a summary of that. And this is what is known as Nuclide notation. So there are two primary ways that we can identify an isotope using shorthand. One of the ways is simply using the elemental symbol and its mass number. So for example, we could use carbon 13 to describe an isotope of carbon. That isotope of carbon has a mass number of 13. In this particular notation, we could transform this into, since 13 is the mass number, that is the number that's on top. Since X is the symbol, we could also abbreviate it in this way, or if we include the atomic number also, since carbon is element number 6, we could give it notation like this as well. So all three forms are common for identifying isotopes. And again, the notation here is based on three abbreviations, three symbols essentially. You've got the elemental symbol here. It directly relates to the atomic number because again, atomic number, number of protons, that is the identifier for the element. So these two inform each other. And then separately, we have the mass number, which gives us specific information about how many neutrons and protons there are. And this will actually give us a lot of information about stability. And again, more on that in chapter 16. So what I want to do now is let's get a little bit of practice on using proper notation to help us to find and identify isotopes. So here we are given notation about three different isotopes: chlorine 35, carbon 11, gold 198. What we want to do is we want to know the number of protons and neutrons in each of these. Now for protons, which we can abbreviate as P+, we know that those are equal to the atomic number Z. Atomic number Z for chlorine is 17. So that one's pretty easy. Neutrons, on the other hand, N0 for the fact that the neutron has no charge. We would need to take the mass number A minus the atomic number Z. So 35 minus 17 would give us 18 neutrons in this isotope. So determining protons and neutrons from this notation is really pretty easy. Protons I get directly from the atomic number. So for carbon 11, that would be 6. Neutrons I get from the subtraction of the mass number minus the atomic number. So for carbon 11, that would be 5. For gold, protons, I would have 79. Neutrons, I would have 198 minus 79, which you can do that in your head if you wish, or you can just punch it into your calculator. 119 will be the result either way. So this covers the nucleus. What about electrons? To answer the question about electrons, what we have to consider is that if we are told no information about charge here, we have to assume then that the charge is neutralized, which means in each of these cases, protons and electrons would have to be equal. So if I was asked about electrons, it'd be 17, 6, and 79. For these three isotopes, assuming that they are neutral charge. If they're not neutral charge, we would be given an indication, +1, -1, +2, -3, whatever. And that would tell us which side it is skewed to and by how much. So if I have a positive charge, that means I have more protons than electrons. If it's negative, I've got more electrons than protons. Since the proton number cannot change without changing the identity of the element, it'd be the number of electrons that would potentially move. All right, I want you to try this one yourselves. I've got 3 symbols here. I want you to complete them, complete the table. So I've got an unidentified isotope of lead. Can you complete its symbol and determine the protons, neutrons, and protons, mass number, and atomic number? From an atomic number and mass number, can you determine protons, neutrons, and symbol? Can you identify an atom based on its mass number and number of neutrons? So take a couple minutes, go ahead and try this. Let's take a look at this first one together and see if we can't maybe resolve some of the problems. We're all kind of sitting there staring at the paper. I don't know if we all know exactly what to do. So for the first one here, lead. Since we know its identity, we should know 2 things about it already. Go to the periodic table. What is the atomic number for lead, Pb? It's 82. That means that the atomic number is 82. That also means that the number of protons is 82. Again, symbol, atomic number, and protons are all tied together. If I know one, I know the other 2 automatically if I've got a periodic table in front of me. The only thing that we're missing now is the mass number. And the mass number is the combination of protons and neutrons. So 82 plus 126 gives me 208 as the mass number of the substance. Now to finish off the symbol, I would need to put that mass number and that atomic number in and around that symbol. Now, one really important thing to remember, mass number is not the same as the atomic mass on the periodic table. We went over the reasons why on Monday. Remember, those masses on the table are averages based upon all of the isotopes that exist and how much of each isotope there are. This is just based on this particular nucleus. So with that in mind, I now know the atomic number for my second example. My atomic number is 39. There should be two other boxes I can fill in here based solely on that information. Anyone? Yeah. The number of protons would be the same, 39. And the symbol, element number 39, is Y. Yttrium. With the atomic number and the mass number, we can fill the form, 89 for the mass, 39 for the atomic. The only thing that we are missing is the number of neutrons. And if you remember, that mass number minus atomic number is neutrons. 89 minus 39 would give me 50 neutrons. So someone walk me through how to do this last one, number 3. So we're given just the mass number and the number of neutrons. Okay, so if I take mass number 31 minus the number of neutrons, 16, 15 would be the answer. That would be the number of protons. Once again, protons, atomic number, and symbol are all related. So if I have 15 protons, that means I have an atomic number of 15. 15 on the periodic table is P, phosphorus. So phosphorus with a mass number of 31 and an atomic number of 15. That would be our symbol. So when it comes to these kinds of problems, that's all the information that we need to do. That's all that we need to really put together. Is if we understand the definition of atomic number and mass number, we can directly tie them to our understanding of protons and neutrons. Now again, absent from this table and this example was the idea of charge. So we're going to talk about that right now. Charge comes in when we have what are called ions. Ions are atoms that are not electrically neutral. And that difference in neutrality comes from the number of electrons. It is the number of electrons that are present that drive whether something is going to be positively charged, negatively charged, or neutral. So in all the previous examples, we dealt with neutral molecules. Neutral molecules being the ones that have no charge, and because of that, we were able to say that the number of protons equals the number of electrons. When we have a positively charged substance, we call it a cation. Cations have fewer electrons than protons. Anions, on the other hand, are negatively charged. They have more electrons than in the neutral atom. So there are more electrons than protons. And again, the proton count is going to be consistent for a given element. So if I'm looking at an element of gold, that gold element is going to have 79 protons, regardless of whether it's neutral, positive, or negative. What's going to change is that number of electrons. If there are 79 electrons to match the 79 protons, then it's neutral. It has no charge. But if there are only 76 electrons for those 79 protons, I'm going to end up having a positive charge. In that case, I have a positive free charge because there are 3 more protons, 79, versus electrons, 76. If I had 80 electrons instead of 79, then that would be a negative charge. I have 1 extra electron compared to proton. But the number of protons doesn't change in any of those circumstances. So let's put this into action. What we want to do is write the number of protons and electrons for these ions. Now the proton part should be pretty easy, because after all, it doesn't change. We just need to go off of the identity. So for sodium, it's 11. For chlorine, it's 17. For oxygen, it would be 8. For aluminum, it would be 13. For phosphorus, it'd be 15. All of these values are just the atomic numbers for each of those 5 elements based on the periodic table. Since all of these are charged, however, what we need to look at, what is going to vary and change, are going to be the electrons themselves. So in the case of sodium, I have 11 protons. I have a positive 1 charge. So I have 1 more positive than negative. I'm going to have logically then only 10 electrons. Now there is a way to do this. There's an equation that we can use to help us. The equation is this: charge is equal to protons minus electrons. So if you can't follow it from a logical standpoint, you can calculate it algebraically. We could rearrange this for electrons. Electrons are equal to protons minus charge. So for something like number 2 here, we have 17 protons and a -1 charge. 17 minus -1 will give us 18 electrons for the chlorine. So Either way that you want to handle it, you can do it algebraically, you can do it logically. Either way works. For oxide here, I'm going to have 2 more electrons. So if I add that 2 to the 8, I would get 10. For aluminum, I have 3 more protons, so 13 minus 3 would give me 10 also. For phosphorus, I'm going to have 3 more electrons. 15 plus 3 would give me 18. Right, any questions with assigning charges and looking at protons and electrons? All right, let's try another practice problem, a different way of looking at this. What is the symbol for the ion that has the following number of protons and electrons? If I have 20 protons and 18 electrons, what would that look like? So for 20 protons, again, you go straight to the periodic table. 20 protons is Ca, that's calcium. So there's our symbol. Now we just need to assign a charge to it. Again, we can go about this mathematically or logically. Logically, I can see that there are 2 more protons. Protons have a positive charge. This is positive 2. I could also just simply plug those values into that equation. 1 minus 18 is positive 2. I could get the charge that way as well. For number 2, 16 protons, 18 electrons. I go to the periodic table. Element number 16 is S, sulfur. 16 minus 18 would be negative 2. So the charge on the sulfur here is negative 2. Number 3, 26 protons, 23 electrons. I go to the periodic table. Element number 26 is Fe, iron. 26 minus 23 is positive 3. So that would be the charge on that iron ion. Right, any questions for problems like these? All right, so let's talk about the periodic table then. So the periodic table has a very particular arrangement to it. It's been arranged in such a way that we can very quickly determine a lot of information about the elements on it. We can break it apart into metals and non-metals. We can identify groups of elements on the table that have similar chemical and physical traits. Now, let's go over a little bit of terminology. The horizontal rows on the periodic table are referred to as periods. This is where the periodic part of the periodic table comes in. Each of those rows are referred to as a period. Each of these vertical columns is referred to as either a group or a family. And it is these families that we want to spend a good bit of time focusing on, because those are the ones that ultimately obey and have certain kinds of familial characteristics. So if I look on the periodic table, any one of those columns, I'm going to find elements in it that have similar kinds of properties in some way, shape, or form. The periodic table is governed by something called periodic law. Periodic law just basically establishes the idea of these families. It says that as we go from row to row to row, the elements in the same column constitute and have similar kinds of chemical properties. And so I have given you a periodic table with which to work. And on that periodic table, we're going to have to do some addition to it to make it a little bit more useful to us. So some of the stuff we've talked about already. We talked about the idea of the periodicity, the fact that as we go from row to row to row, the ones in the individual columns all seem to line up with similar properties. We talked about the idea of atomic number and atomic mass being involved in the table itself. The distinguishing between metals and nonmetals and metalloids. Well, your table actually has that involved in it as well. If you look closely at your table, I'm going to back up a slide here. You should see on your table a thin black line that splits between boron and aluminum and kind of staggers its way down like so. That line represents the division between the metallic elements and the non-metallic elements. Over here on this side of the table, we have our metals. Over here on this side of the table, we have our non-metals. The elements on the line itself, which in this table here are the green ones, these are the metalloids. The ones that have similar properties to both metals and non-metals. So on your table, you already have that information kind of stashed in there. You might want to go over it again just to kind of highlight it a little bit more deeply. But that's what that black line that seems to be a little bit thicker than the others represents. So just based on position on the table, we can determine, okay, this is the metal, this is the non-metal. So we don't have to memorize lists of metals and non-metals, of metalloids. But if we're looking at a periodic table, we can get that information. And once again, the elements in the same family possess similar kinds of properties. Now, before we get to the 5 families, there's one other piece of labeling that I want you to do on your table itself. You'll notice that on your table, across the top of each one of the columns, there is a number, 1 through 18. That is one of the ways that we mark the columns. So we refer to them by their family number. So the oxygen family is in group 16. The alkali metals are in group 1. Now your book and other references we'll often refer to something called the CAS numbering system. CAS numbering system uses a series of A's and B's to identify groups as well. And so what we're really concerned with are the A numbers. So what I want you to do is label those 8 big columns, not the ones in the middle, but those 8 big tall ones, from 1 to 8. 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. That is the CAS numbering system at work here. And when we reference families, we're going to make reference to its CAS number group. So let's talk about 5 common families. The first of the common families is the group 1A. Group 1A is known as the alkali metal family. Inside of the alkali metal family, you're going to find everything in group 1 other than hydrogen. Hydrogen is put in that group because it doesn't have some similar activity. It's something similar on the alkali level, but it's not actually a gas. It's like gas. And I'm we're at least generally included among the alkali metals. But the important thing about this group of metals is their reactivity. Their reactivities are very, very unique. They react explosively with water, and they ignite with air. That's what makes them unique. They're very, very reactive metals. Let's take a look at our second family. Second family is right next door, group 2A. Group 2A are the alkaline earth metals. Alkaline earth metals are similar in that they react with the air, they react with water, but they don't do so nearly as violently or nearly as explosively. So we can think of the alkaline earth metals as kind of a less powerful version of the alkali metals. Still reactive. In fact, these are called alkaline earth metals because these metals make up a good chunk of the stuff that we can dig out of the ground. That's where that reaction with oxygen comes into play. But they're not nearly as dangerous. They're not nearly as reactive. They're not nearly as explosive. But like the first group, they will react with air. They will react with water. The substances that they make when they do those reactions generally are basic substances, which is why they carry the name alkaline or alkali. That word means base. So those are the two most reactive families on the metal side of the line. Let's take a look at some common non-metal families. Group 6A, the oxygen family. Oxygen family is sometimes known as the chalcogen. In here you have your oxygens, your sulfurs, your seleniums, and then to a much lesser extent your telluriums and your poloniums. These substances are moderately reactive. We know that oxygen reacts with a whole lot of stuff, but a lot of the reactions that oxygen undertakes are slow. For example, we know that oxygen reacts with iron. It causes rust. But we also know that that process doesn't occur in seconds. It doesn't occur in minutes. It doesn't occur in hours. It takes days, weeks, months for rusting to really show up enough for us to notice. So we know it's reactive, but we also know that it's not terribly fast in its reactivity either. And as you go down the line here, they get less and less reactive in that respect. Which is why the majority of materials that we see from this family come from either oxygen or sulfur. Selenides, tellurides, they exist. They're far more rare. Group 7A, these are the halogens. The halogens are kind of like the alkali metals, highly reactive, but non-metallic. So in this family, you have your fluorines, your chlorines, your bromines, your iodines, and again, to a lesser extent, your acetylene, and your tennessine. But these substances are really reactive. And again, it kind of starts top down. Fluorine is the most reactive of the group. Fluorine is next, bromine is next. It's no surprise then, given the reactivities, that a lot of the combinations that we see can be between halogens and alkali metals. You have your most reactive metal and your most reactive non-metal. If they get into the same room as each other, usually something is going to happen. And then lastly, we're going to talk about something that is completely different. Group 8A, the last group here. These are our noble gases. What makes them special? Is that they are not reactive. So unlike the other ones in the other four families that we discussed, alkali metals, reactive. Alkaline earth metals, reactive but less so. Chalcogens, reactive but less so. Halogens, extremely reactive. Noble gases, not reactive. Really not at all. There are a couple of them, krypton and xenon in particular, that we can get to react if we put them with something that is strongly reactive enough. Usually it's chlorine. But even then, the substances that they create are incredibly unstable. React with even a single drop of water. So these are the five families, and this is where we're actually going to kind of close things out for the day. So on Friday, bring your tables with you. We're going to continue to add to them. And then we're going to get into talking about how we go from atoms, individual elements, to compounds and molecules. And that'll be the subject for Friday's lecture. But until then, have a good day. I'll see you next time.